Thank you.
Okay, my name is Toye Onikoyi, and we are the Animatronic Stick Figurine team. I would like to thank our technical director, Dr. Sodi.
I'm Stephen Fonts, computer engineer of the team. I would also like to thank Professor Shunyan. This was not me or Toye's first choice for design, but I'm glad we got it. So, we're the last URI Capstone team, so let's give a round of applause to Dr. Shunyan.
So our main objective is to create a real-life physical robot that's driven by data sent from a user application. Now, our user application has two modes. It has a live stream mode that allows data to be sent from the application in real time, and we have a frame-by-frame mode that allows the user to create an animation sequentially in parallel. And we wanted our application to be really interactive. We wanted the user to have full control over the robot. So we have 14 servers incorporated. The motivation for our project is to really for it to be really fun, entertainment, and we want it to be a consumer product that can be sold.
As far as the task distribution goes, I was in charge of the visual design of the application, as well as the major source code of the formulas of how the robot is going to visually be depicted, and applying the products for the physical robot.
And I created all the 3D modeling. I used Blender. It's a computer graphical software. It's a really good tool for 3D modeling. I also created the user application. I created all the components inside of it. The windows, there's an embedded 3D window. And the animation development, I created a sequential parallel animation that the user are going to create.
Alright, so this is my original drawing in my logbook. See, Professor, I used a logbook. So what we have here is this 3D environment, a window into a 3D environment that's embedded into this 2D frame. This is what you're going to see when you open up the application. Now, this semester, this is what we focused on. We're not actually building it yet. We're going to save that till next semester. So we have these slider bars that Toye created, and you're going to be able to walk up and slide this to the left or right, and you're going to get feedback of the head actually turning left and right. There's 14 servos. Some of the joints can move in multiple directions, like the arm, for instance, can move like this or like this. So the leg can go like that, out to the side. You're going to be have a good amount of dexterity, more than you would see at like a Brookstone, where the robots are pretty rudimentary. Yeah, so that's that.
So one of my main tasks were to create the 3D models, and this is not our first model. This is our latest model. Our first model is really
Look like a trash can, man.
basic. This is our latest model. It might improve, but it incorporates different components that we based off the servos. So each part needed to have a servo component. But what you cannot see inside this 3D mesh is a hierarchic interconnection of bones. Now, we needed those bones in Blender to animate our figure, rotate it, transform it. But we ran into some problems when exporting the mesh from Blender into our application. The character exported correctly, but the rig, the interconnection of bones did not. So we needed to find a new way to animate the character. So we ended up having to separate each individual part represented from a servo into their separate parts in Blender.
So we have 11 objects: the head, chest, pelvis, upper legs, upper arm, and the lower arms. That's 11 total. And we kind of had to create our own mini 3D game engine. We don't have anything existing to take care of this, so we had to make everything from scratch. Now, there's two formulas that we used a lot of. It's a rotate and a translate. So rotate is like, let's say, any way like this, and we use translate. I'm going to talk about that next, but that's just to move in space. So this is an example of the source code that we made, and you just give it a name, and what's the angle. Now, those slider bars are usually from 0 to 90 degrees, or 0 to 180 degrees. You just read that, and you give it an axis that you want to rotate it on. So I have a servo, and I want to rotate. This would be the x-axis right here. But we had problems with that because the x-axis is actually right here, So if I were to rotate this on the x-axis, and I want to go like this, that wouldn't happen. Actually, his whole bicep would just detach from the robot and rotate all the way around the world, not in place, which was a huge problem. Which was like, that's not good, what are we gonna do? So I was actually contemplating dropping out of college and joining the army, but
so went back into Blender and decided to translate all the separated parts to the origin. And now we needed to make a rotational point. So we defined a rotational point for each separated part. And this was in the 3D space. So it was at the origin, 0x, 0y, 0z. So we made each rotational point the origin of the 3D space.
So now we can rotate it how we want. But if you were to put all these objects together in one environment, they would just be piled on top of each other at the origin, which is not what we want. So we use this second formula to just shift it in space. Now, I could just put just the literal values in here to get it back to build, but we need to do a lot more than that. We need to translate it to describe what happens when you're moving these slider bars to take care of all of that. So I'm going to give you an example of some source code. This is pseudocode. The source code actually looks a lot clunkier than this, but this is just the X component of where this is just X I'm all dealing with of the elbow. And when I say elbow, that's this piece right here. And it's like simple trigonometry, but it gets a little complicated because the whole arm can move in two directions, like this and the body. So this piece actually depends on two servos, which depends on another servo. So it can get kind of complicated. This is just the X, there's a Y and a Z, but it's just more of the same of this stuff. And this exists for every part of the body.
So the materials we used was a servo motor driver, Arduino Nano, power supply at 5 volts. A digital servo, we were using 14 of these, and these were like the smallest ones we could find. We found ultra mini servos, and since it's 14, we need to find really small ones. And the total came out to around $475.
That's not even paying us, it should be like $50,000. All right, so this is how it's going to work. It's really simple breakdown. The user comes up. This is what we're working on this semester. We bought these parts. This is our Arduino Nano. We needed that to be small because the robot's going to be about, I don't know, a foot tall, under a foot tall. So the user defines the motion. If we're in live stream mode, it's just going to send it and forward it to the robot. But if, let's say we're going to make an animation, we're going to have different frames to go from A to B to C to D, which is going to forward that data to the Nano, and the Nano's job is going to be to decide how to get from A to B to C to D with all the different servos. We don't have enough I/O capacity on the Nano to house 14 servos, so we bought this servo controller board, which can hold up to 16 servos. It was actually pretty perfect that we got it. The servos take about 600 milliamps each. So we needed that additional power supply. This is the 5-volt, 10-amp power supply. And this is physically connected to the servos that are mounted in the robot that we're going to create. And we have a demo.
So this is our user application. We created it in C++ and QML code. Just gonna go through it really. We have slider bars, and each slider bar represents a servo. This huge slider bar at the top is the camera, and you can see it rotates the world around the robot 180 degrees each way. And you could literally just change the values of each servo, and the robot will move. Now, this will be live stream mode. We have 2 modes. So basically, whatever we define here, the robot will act out in real time. So you just kind of see. And we created a button to bring that back to default. And right here, is our frame by frame mode. So the user can define a pose. Something
the left leg forward. And then show what the hip does. Oh, it's up.
And basically the final frame, set a duration time and then enter it in. And frame by frame, the user can create that animation. And we do have some predefined animations that the user can create. These are just some predefined ones we made. And this button does a little wave.
So actually his animations are directly controlling the slider bars, which then control the objects in the 3D world. So it's pretty cool to see the slider bars move as feedback. Yeah, it looks pretty cool. He's a dance move that Toye does himself. It's pretty cool. It's like, I would like to play with this.
Yeah.
Would you guys? Like, yeah, you would.
That's our project.
Thank you very much.